Negative 90 degrees Celsius. Liquid nitrogen and dry ice. Has more ductility fracture, but still brittle. Negative 72 degrees Celsius, dry ice. Steel on the left still, aluminum on the right. It's always every picture like that. Still very brittle, some ductility fracture. Negative 42 degrees Celsius, dry ice and ordinary ice. Almost the same as the last picture. Getting more ductile. 0 degrees Celsius, ordinary ice. That's starting to get more ductile fracture, but still brittle. And steel is transitioning. Room temperature, 23 degrees Celsius. Steel, getting ductile. Shear lips are present. Aluminum, some more ductility, but still brittle. 90 degrees Celsius, boiling water. Very ductile fractures. And finally, 188 degrees Celsius in the furnace. Very ductile fractures. Shear lips are present. Brake plane is not smooth. So now, we compare carbon steel 1045 at negative 186 degrees Celsius to 188 degrees Celsius. You can see from the shear plane, brittle fracture plane is more smooth. Shear lips, very uneven, very brittle, very ductile fracture here on the right. Compared to aluminum alloy, very brittle, fracture plane is smooth. More ductile fracture, yet shear plane is smooth. The shear lips are present. This graph shows the energy absorbed by steel along the temperature range. Transition temperature, negative 77 degrees Celsius from experiments. R value almost 1. Aluminum alloy, energy absorbed by degrees Celsius, almost very linear. This is the intersection of steel and aluminum alloy. Energy absorbed versus degrees Celsius. They intersect at negative 66.5 degrees Celsius. This here, the bar graph. Blue, carbon steel. Red, aluminum alloy. The aluminum alloy, very consistent across. Steel, transition temperature, you can tell happening between negative 42 and 0 degrees. Summary of results. Tests reveal a high degree of temperature dependence for carbon steel. At a higher temperature, the steel exhibits a more ductile fracture mode, which results in more energy absorbed. Aluminum alloy was less temperature dependent. The energy absorbed was almost linear across the temperature range, which displayed a more ductile fracture at higher temperatures. Final remarks. You, sir, what is your GPA?
4.0.
Get out. Third degree in the trash. You, sir, what is your GPA?
4.0.
Get out. Third degree in the trash. Do you not know materials? Then get out. Do you not know that steel is tough? And you put enough pressure, it breaks. Thank you, everybody. Victorious and glorious students for listening.
Any questions from students? Okay. You're talking about brittle and ductile fractures. What is the difference between brittle and ductile fractures?
Like, what's the definition between brittle and ductile?
Yeah, what is the definition of brittle? What is the definition of ductile?
The ductile is more malleable, brittle. When you apply a force, it breaks very easily. It's weak.
The material that I gave you was T3, A224, T351. What is T351?
T3 describes the heat treatment process.
Did you see what it is?
I think they just raise the temperature high and let it cool down at air temperature.
What is the application where we suggest that you use 2024, and what is the other one where we use the steel? The application where you use steel, where the application where you use
The little application for steel you use in cars, hydraulic clamps, something where the temperature is not ranging very far, whereas aluminum we can use on airplanes because it goes to like negative 30 degrees Celsius, you know, when you're 35,000 feet. So the temperature drops, so you can't have a transition temperature where it gets very weak and brittle. You still need those ductility properties of aluminum alloy.